Hi and Assalamualaikum. My name is AINAL ARIFAH binti JAFFAR and my matric number is B1323100165. So today me and my group mate will present about the IoT-based smart HVAC system for the BMKH4313 project management. So for the HVAC problem statement is HVAC system are major contributor to electrical energy consumption in modern building. Many conventional systems operate using fixed temperature, set point and predefined schedule without real-time monitoring. This lack of continuous performance and environmental monitoring often lead to inefficient energy uses, overcooling, poor indoor air quality and increased operational costs. Issues such as elevated carbon dioxide (CO2) level, improper humidity control, airflow imbalance, and system faults are frequently detected only after occupant complaints occur, resulting in delay maintenance and prolonged system inefficiency. Therefore, there is a need for a smart and cost-effective HVAC monitoring solution that provide real-time data, enable early fault detection, and support energy efficient and sustainable building operation. Next, proposed IoT-based smart HVAC system. The proposed IoT-based smart HVAC system is designed to enhance energy efficiency, indoor air quality, and system performance through the real-time monitoring and data analysis. The system integrates multiple sensors to measure key parameters such as room temperature, supply and return air temperature, relative humidity, carbon dioxide concentration, energy consumption, and filter pressure drop. Sensor data is collected and processed using a microcontroller such as ESP32 or Arduino and transmitted via Wi-Fi to a cloud platform for storage and analysis. User can access real-time and historical data through a web-based dashboard, enabling continuous performance monitoring, yearly fault detection, and informed decision-making. This system supports improved HVAC operational efficiency, reduce energy consumption, enhance occupant comforts, and sustainable building management without requiring major modification existing HVAC infrastructure.
My name is AZWANIE binti AZMEE. I will be presenting about WBS, which is work breakdown structure. It decomposes the project into manageable components to ensure complete coverage of the project scope and effective control of all activities. The WBS is developed based on project objective and form of the foundation for scheduling, responsibility assignment, and cost estimation. So we have level 1, IoT-based smart HVAC monitoring and energy optimization system. Level 2, system planning, system installation and development, system integration and testing. And lastly, the project closure. For the level 3, the first one is the system planning, which is sensor selection, system architecture planning. Second is system installation and development, which is sensor installation and wiring, dashboard development and data visualization. The third one is system integration and testing, which is system integration, functional testing and validation. The fourth is project closure, which is final evaluation, project documentation and reporting. Next, I will talk about organization breakdown structure, which is OBS. It defines the project team structure and clearly assigns responsibility to each member. This ensures effective coordination, accountability, and timely completion of project activities. Each member is responsible for specific technical and management tasks aligned with the work breakdown structure. The first role that we have is project supervisor, academic advisor. The responsibility provide technical guidance and project approval, review progress and provide feedback. Second role is project leader. The responsibility is overall project coordination and planning. Second is ensure project objective, scope and timeline are achieved. Third is coordinates between hardware, software and documentation team. The third one is hardware engineer. The responsibility is selection of HVAC related sensor. The second one is hardware wiring and sensor integration. The third one is calibration and hardware testing. The fourth one is the software engineer. The responsibility is microcontroller programming. Second is data acquisition and Wi-Fi communication. Third is dashboard and data visualization of development. The fifth one is documentation and cost analysis. The responsibility is report writing and formatting. Second is cost estimation and budget justification. The third one is preparation and presentation material. Next, for the task list and scheduling. The first activity code is A. The task is sensor selection and system planning. The duration is 3. It start on first day and finish at the third day. The stakeholder that include is project leader or system designer. For the B is sensor installation and wiring. The duration is 5 days. It start on day 4 and end at day 8. The stakeholder that involved is hardware engineer or technician. The activity code for C is the dashboard development and data visualization. The duration is 7. It starts on the 4th day and ends in the day 10. The stakeholder is software developer. Next, for the D, it is system integration and functional testing. The duration is 4 days. It starts on day 11. It ends on day 14. The stakeholder that involved is project leader and technical team. Activity code for E, which is the task is final evaluation and project documentation. The duration is 2 days. It starts on day 15 and finish at day 16. The stakeholder is project leader and documentation team.
Hi, my name is FARID HAKIMI bin KARIM. My metric number is B1323101117. Okay, right now I will share about the network diagram. The project starts with sensor selection and system planning, which take 3 days. In this phase, suitable sensors are selected and the system architecture, objective and requirements are defined to ensure the project is well planned. Next, 2 activities are carried out in parallel. Sensor installation and wiring phase B is conducted over 5 days, focusing on installing sensor and completing all electrical wiring. At the same time, dashboard development phase C takes 7 days, where the monitoring interface and data visualization dashboard are developed. After both phase B and phase C are complete, the project moves to system integration and functional testing, which lasts 4 days. During this phase, all hardware and software components are integrated and functional testing is performed to ensure the system operates correctly and reliably. Finally, final evaluation and documentation phase E is carried out over 2 days. This phase involves evaluating the system performance, validating results, and preparing the final documentation. Next, critical part. The critical part in project management represents the longest sequence of dependent tasks that determine the minimum project durations. Identifying the critical path is essential for effective scheduling, resources allocations, and timely project completion. This diagram illustrates the scheduling and dependence of tasks within a project using a network format. ES, early start, the earliest time the task can begin. Duration, the total time required to complete the task. EF is early finish, the earliest time the task can be complete. Critical part. The task label C, dashboard, is marked as critical. This means it lies on the critical part, the sequence of tasks that determines the shortest possible project duration. Any delay in this task will directly delay the entire project. Slack time. Task B, installation has a slack of 2. Meaning it can be delayed by up to 2 times unit without affecting the overall project completion date. Slack provides flexibility in scheduling non-critical tasks. As we can see, have task A, B, C, D, E. A. Planning, B. Installation, C. Dashboard, D. Testing, E. Evaluation. This diagram help project manager identify which tasks are time sensitive and which have scheduling flexibility, allowing for better resource allocation and risk management. For the cost estimation, the item, temperature and humidity sensor, the estimate cost is RM40, CO2 sensor RM180, energy meter RM100, microcontroller or ESP32 RM40, cloud platform and software RM50, miscellaneous components RM60. The total estimate cost for this project is RM470. Next, we go to expected benefit. First, energy. Real-time monitoring of HVAC energy consumption, identification of inefficiencies such as overcooling and excessive compressor operation, data-driven optimization of HVAC operation, reduction of unnecessary energy usage, and expected energy saving of at least 10%. Second, indoor air quality. Continuous monitoring of CO2 concentration and humidity. CO2 level maintained below 800 ppm for adequate ventilation. Relative humidity control within 50 to 60%. Early detection of poor air quality conditions and improve occupant comfort, health and productivity. Third, maintenance. Continuous visibility of HVAC system performance. Early detection of faults. Shift from reactive to preventive maintenance, reduce system downtime and maintenance costs, extended HVAC equipment lifespan.
So, for the conclusion, the IoT-based smart HVAC monitoring and energy optimization system proposed in this project provide an effective approach to improving HVAC system performance in building environment. The system enables real-time monitoring of key parameters such as temperature, humidity, carbon dioxide level, and energy consumption, allowing continuous data and supporting informants. Data-driven decision-making. The implementation of this system helps reduce energy consumption, improve indoor air quality, and enable faster detection of HVAC system fault. This benefit contribute to minimize operational inefficiency, enhancing occupant comforts, and reducing maintenance delay. Overall, this project demonstrates that the integration of IoT technology into HVAC system can significantly improve system efficiency, reliability, and sustainability, while supporting smart building and energy efficient building management initiative. Thank you.